So I want to kind of go through like it's a sort of like an aspirational list of problems we can solve using recursion. Or a recursive technique, right? All right, so one I think is interesting are certain sums. And for instance, right, this is a fun one to do, but then you're like, okay, well, what if you did the sum of cubes, right? Is that harder? What is that? All right, what's the formula for that? A lot of people know the formula for this one, but how about other ones? And how about for any power? And there's plenty of other sums too that you could play with. It just comes down to which one you're interested in. I'll show you how to do that. There are certain kinds of models can be built. And studied. You may not be able to get a solution to the equation, but I think one that's really important would be some sort of SIR, a discrete version. Considering the pandemic, you can do discrete versions of SIR models, which in some sense are a little bit more realistic than the differential equations versions. The continuous or differential equation versions of the SIR models are actually just easier to solve or easier to run analyses on. But if you do the discrete ones, you can at least run things through, and the discrete ones also are quite useful. In a very ironic twist, even the differential equation, all differential equations solvers, I shouldn't say all, but I'm going to because it's got to be true. All the ones I'm aware of, so all differential equation solvers actually convert the differential equation to a difference equation in some sense, and so all differential equation solvers are recursive. Now, it may be adaptive in some sense where they kind of change the recursive tool based on the phenomenons that are going on, but these are, nonetheless, they're still recursive solvers. So it's kind of interesting. Newton's method. Finds solutions to f of x equals 0. It'll actually find the x's that solve this thing. So it's a root finder. Okay, another method of finding roots is doing a binary search, right? You just use the intermediate value theorem, and then you kind of just go back and forth. That's an exponential finder, but it turns out Newton's method is faster than that. Newton's method is actually super exponential in the way it goes. So I don't think it's worth throwing Newton's method out as an important tool. All right, and then if you're interested, this is more just recreational, but if you want to make things called Julia sets, or the Mandelbrot set, and this is plural, Julia sets. There's the Mandelbrot set, which is singular. Which in some sense, well, anyway, I don't want to get too deep into this, but Julia sets and the Mandelbrot set, to build these things, you can use recursion. Very simple recursive formula. You get remarkably beautiful pictures. Mandelbrot set uses one particular recursive rule, but then it modifies a parameter. Julia sets, you can do all kinds of different recursive rules and build Julia sets based on those. And this is just this is kind of like a starter's list of sorts of problems you can address and approach using recursion, or problems that recursion solve. Maybe I'm not saying it the right way there. All right, so I have a little bit of room here, so I'd like to at least start with this first bullet here and show you what those equations look like. So one of the tricks you kind of have to develop, and this sometimes is easy and sometimes it's quite hard, is how do you build your what you're trying to solve, how do you interpret your problem as a recursive one. And this first bullet definitely has it in there. So how could you do that? So let me kind of decompose this first one. So suppose our task is to find a formula for 1 plus 2 dot dot up to n, right? The sum of the first n integers. How do you find a formula for that? Well, there's lots of cool tricks out there. You can actually use induction to prove that it's the right formula, but let's do something better. Let's actually come up with a process that finds the formula. All right, so I'm going to do this using recursion, obviously. And I'm going to start, because my first number is a 1, I'm going to start using the first thing as my starting seed, right? So use f's, so f1 will be 1. And then how do I get to my next one? Well, for instance, f2 would be f1 plus 2. And I'm doing this on purpose to make sure I get things right. Okay, and then f3 is going to be f2 plus 3, right? This would be 1 plus 2. And f2 is 1 plus 2. That's f2, and then plus 3. Okay, so in general, fn is fn minus 1 plus n. Or, if I don't want the minuses in my indices, fn plus 1 is equal to fn plus n plus 1. Okay, this one's probably just a little bit more natural to come by because of the nice matches there with kind of the where you're at and where you came from. But you can also look at it from the perspective, right? Maybe you're at f2 and this is the where you're going. Notice these are the exact same equation. And if you want to modify, jump from having no minuses to having all pluses, or from all pluses to just minuses in the indices, just make sure you change every single index variable appropriately. Right. So this is the recursive equation. All right, now, usually I would solve this one. This is my preference. You can actually do either. When it comes to solving them, it just comes down to preference, and that's my preference. We're going to do a process that is kind of in 2 stages. Well, this will be a whole part of it. I move the fn over, and we're actually going to do 2 parts of the solution. There's going to be a part of this that has nothing to do with n plus 1, and then there's going to be another part that gives us the n plus 1 chunk. So I know it looks funny right here, but then we put those pieces together, and then we'll have a full solution. So keep in mind, there was an initial condition here. F1 was 1. Okay. So this is the difference equation, if we could possibly solve it, which we will be able to. This is the difference equation that models these sums. So Fn equals 1 plus 2 up to n. If we get a formula for Fn, we'll have a formula for the first n integers. Okay, and we'll be able to, this technique is just as good for if you want to use powers or other weird sequential sums. As long as this sum can be written in this way, you can use this technique. All right. These other things are fairly specific gadgets, and sometimes the solving process may actually be useful in these areas, and sometimes it just won't apply at all. We'll be able to solve what's called linear difference equations, and many of these are not linear. Yeah, we'll look at the ones I can see, yeah, and very few of these are linear. All right, so next video we're going to work on solving these things, solving difference equations, and then once we have that, we can come back and actually do some of these cool tasks with it.